Welcome back to the Deep Dive. We're here, as always, to take dense source material and really turn it into useful knowledge for you. Basically a shortcut to getting smart on complex topics. Today, we're stepping away from the usual sources. We're heading into the wild, you could say. Metaphorically, anyway. We're looking at survival shelter construction.
Yeah, and not just any shelters. We're diving into the specific methods from a source known as Brotherwood. Very refined techniques.
Exactly. This isn't your basic weekend camping lean-to. It's more like, well, it's an exploration of high-level primitive technology. It demands efficiency, real insight, and a deep connection with the environment. So our mission today is pretty clear-cut. We're extracting the core knowledge behind 3 distinct, very specialized wilderness shelters.
Highly effective ones.
Right, highly effective. And the key constraint, they're built using only natural materials, stuff you find right there in the forest.
No hardware store runs.
None at all. We want to get the why and the how behind these specific designs. It's kind of a fast track to understanding some pretty sophisticated natural engineering principles.
And the sources we have are actually quite detailed. They don't just show the final structures, they really get into the philosophy behind them.
Which is interesting in itself.
It is. So we're looking at 3 main designs. First, the elevated platform that's built for dealing with damp ground, snow, that kind of thing.
Okay.
Second, the insulated structure. This one's engineered to create its own little microclimate, basically a pocket of warmth.
A personal furnace, almost.
Sort of, yeah. And third, there's the durable A-frame. This one's often built on snow hills, designed for serious resilience against weather and tricky terrain.
Got it. Elevated, insulated A-frame.
But crucially, the sources stress that just knowing the designs isn't enough. The physical build has to be backed up by, well, foundational skills.
Like what?
2 main things. 1, absolute mastery of fire starting. We're talking reliable fire in any conditions.
Okay, that makes sense.
Yeah.
Heat is critical.
Absolutely. And 2, a really smart, sustainable approach to getting your resources, your wood mainly.
Sustainable. We'll need to unpack that.
Yeah. Without those pillars, fire, and resources, the best shelter design is just, well, it's just a cold frame.
Yeah.
It doesn't do you much good.
Okay, so here's the real hook, I think, for you listening. Brotherwood's philosophy, it seems, argues that real survival skill isn't just about toughing it out. It's not about panic.
No, quite the opposite.
It demands patience, a deep practical respect for nature, and this trained eye. The ability to look at what most people see as just forest debris, a branch, a rock, and see it instantly as a tool, a resource, an opportunity.
Seeing potential everywhere.
Exactly. Okay, so let's unpack that first. Let's apply that mindset right away. We're talking about building shelters meant to last, shelters that genuinely keep you alive.
Yeah.
We probably need to start with that worldview, right? The one that makes that kind of precision possible.
Right. Section 1 really gets into this synergy. It's about blending ancient building knowledge with modern survival science.
Okay, ancient wisdom meets modern know-how. What does that look like in practice?
Well, think about ancient techniques. That implies generations, maybe thousands of years, of learning through trial and error, indigenous knowledge about what works structurally.
Like which local wood holds weight best.
Exactly. Or how to orient a structure against prevailing winds. Knowing which bark repels water, like birch bark being naturally oily, it's knowledge deeply tied to the specific local environment tasked down.
Okay, I get the ancient part. So where does the modern survival expertise come in?
That's where we bring in the physics, the efficiency principles, especially thermodynamics.
Ah, so it's not just build strong, it's build warm efficiently.
Precisely. Modern science lets us understand and quantify heat loss, conduction, convection, radiation. We know, for instance, that losing heat directly into the cold ground, conduction, is often the biggest threat to staying warm.
So you design specifically to counter that, like that elevated platform you mentioned.
Exactly. It's a direct application of understanding thermal breaks. So this blend, the synergy, it leads to building with insight and flexibility.
Meaning you're not just rigidly following instructions.
Right. You're adapting. Say you find a big piece of dead wood that's already naturally curved in a strong way. You don't ignore it because the blueprint calls for straight poles. You use that curve. It becomes a structural rib.
So you're working with the forest's materials, not just imposing a design on them.
Yes. That makes the build faster, uses less energy, and the final structure is often stronger because it leverages natural forms. The forest becomes your partner, your supplier, not just an obstacle course.
Okay, that philosophical shift makes sense.
Yeah.
And it leads right into this idea of mindset, particularly patience. Why patience? Survival stories always seem to emphasize speed, urgency.
Yeah, the panic narrative. But the source material here is really clear. Rushing a survival shelter is probably the quickest way to make it fail. Think about lashing. That's how you join poles together, right? Primitive nails and screws, basically. If you rush your knots, your figure eights, or square lashings, they'll be loose.
And loose joints mean?
Weak structure,
Yeah.
add some wind load or heavy snow, and those joints give way. The shelter collapses. Now you've wasted energy, lost valuable time, and you're rebuilding in potentially worse conditions.
So patience allows for doing it right the first time. Checking the tension, using the right thickness of cordage.
Meticulously. It's the absolute foundation of a durable, reliable structure. And that ties into the next point, respect for nature.
Which sounds nice, but what does it mean practically when you need to build shelter now?
It's highly practical. It means sustainable wood gathering. Brother Wood's approach is quite strict on this. You don't cut down living trees unless it's an absolute last resort for a critical long-term structure.
Why not? Green wood is wood, isn't it?
Well, first, cutting green wood takes way more energy than processing dry deadfall. It's tougher, heavier. Second, green wood is full of moisture. You bring that into your shelter, walls, or frame.
And you're basically building a damp, cold structure that wakes heat away.
Exactly. So sustainability here means prioritizing deadfall. But not just grabbing any dead stick, you have to assess it.
Assess dead wood.
Yeah. Is it hard? Dry? Does it make a sharp clack sound when you tap it? That's good structural wood. Or is it soft? Maybe punky? Feels damp?
That's maybe only good for...
Maybe for insulation, like bedding on the floor. Or perhaps just for firewood tinder, definitely not for your main support post or ridgepole. This selective process saves energy and ensures you're building with the best quality materials available.
Okay, so that assessment skill is the seeing opportunity part. Training your eye to see the forest floor, not as random junk, but as like a hardware store.
Precisely. Evaluating everything. That flat, dense rock, perfect hearthstone. It'll absorb heat from the fire and radiate it back slowly through the earth.
Or that branch with a perfect natural fork.
Becomes a key structural joint, maybe supporting your ridgepole. No complex cutting or lashing needed there. It's understanding material properties, strength, insulation value, water resistance that turns random debris into calculated assets.
It's seeing the potential function of the form.
Got it. Now, this brings us to those foundational skills that make these shelters actually livable. Number one, mastering fire starting.
You mentioned that earlier. The shelter is just a box without heat.
Right. And the source emphasizes mastery. This isn't about occasionally getting lucky with a lighter. It means being able to reliably make fire under difficult conditions.
Like in the rain.
Yeah.
Or high wind.
Exactly. It means knowing where to find dry tinder even when everything seems wet. Scraping the inner bark of certain trees, finding resinous pine knots, maybe carrying your own dry tinder bundle.
Skills that let you get a flame going in minutes, not hours.
Which can literally be the difference between life and death in freezing weather. The fire creates the heat, the shelter contains it, they work together.
And the second skill was a sustainable wood acquisition, but more than just using deadfall.
Yeah, it's also about how you process the material you find. Once you've identified that perfect piece of dry, hard deadwood for, say, your main ridgepole, you don't just muscle it around.
Exactly.
You use efficiency. Leverage, maybe breaking it over a rock or another log at a strategic point. Using natural breaks in the wood. Efficient cutting techniques, whether you have a modern saw or a primitive stone tool.
So minimizing effort at every step.
Right. Don't try to drag a massive 20-foot log if you only need 8 feet. Process it efficiently where you find it. Brother Wood's approach suggests a deep understanding of wood grain, leverage points. Ways to make construction less about brute force and more about smart application of energy.
So the quality of the build starts way back with how efficiently you gather and prepare the materials.
Absolutely. It all connects.
Okay, let's move into the core of this now, section 2. The 3 specific shelter designs. These aren't just generic shelters, they're engineered solutions for specific problems, right?
Yeah. Exactly. Specialized tools for specific jobs. Let's start with type 1, the elevated platform.
All right, building off the ground, what's the core idea here?
It's pure applied thermal physics, really. The goal is to lift your sleeping area and ideally the whole floor, a good distance off the ground, maybe 6 inches, maybe a foot or more.
Why? What problem does that solve?
It directly combats 2 major enemies of warmth in damp or snowy places: conduction and moisture wicking.
Okay, explain conduction first.
If you lie directly on snow or wet ground, your body heat is just sucked away into the earth, like putting a warm hand on a block of ice. Snow is actually a decent insulator if it surrounds you, trapping air, but if you're pressing down on it,
Becomes a giant heat sink, pulling warmth out of you.
massively. So the elevation creates a physical separation, an air gap.
That air gap is the key.
It's the thermal break. Still air is a fantastic insulator. Think double-paned windows or a thermos. That gap, especially if you can enclose the space underneath the platform somewhat, creates a buffer of relatively still, warmer air. It dramatically slows down that conductive heat loss into the ground.
Okay, that makes sense for cold ground. What about dampness, the wicking part?
Right. If your bedding or even the base of your shelter walls touches wet ground, water travels upwards through capillary action. It wicks right into your materials.
And wet materials are cold materials.
Extremely cold. Wet insulation loses heat something like 50 times faster than dry insulation because of evaporation. So lifting the structure breaks that connection. It stops the moisture from even reaching your living space.
Smart. So how do you build it? What does it look like structurally?
Usually you need solid vertical posts. You might drive stakes deep or use tripod bases for stability on uneven ground. Then you build a sturdy platform frame on top, like a floor joist system. Brother Wood apparently advises using smaller cross pieces, spaced closely together for the floor. That creates a tight lattice
Why close together?
to support your insulation layer properly. If the gaps are too big, your bedding material, leaves, pine needles, whatever, will sag down, compress, and you lose that vital air underneath. It closes the gap you worked so hard to create.
Ah, got it. So this elevated design is really crucial in wet, boggy areas or places with deep snow.
Absolutely non-negotiable in those environments if you want to stay warm and dry.
Okay, that's shelter type 1. What about type 2? The insulated structures for microclimates. This sounds like aiming for real warmth inside.
That's exactly the goal. We're moving beyond just preventing heat loss to actively creating a significantly warmer zone inside.
What do you mean by microclimate in this context?
We're talking about getting the interior temperature maybe 30, 40, even 50 degrees Fahrenheit warmer than the outside air with very little air movement inside, basically trapping the heat your body and maybe a small fire produces.
Like a little bubble of warmth?
Yeah, essentially. And it's achieved almost entirely through insulation. Piles and piles of natural insulating layers.
What kind of materials are we talking about?
The sources mention things like dry moss, loads of fluffy pine needles, shredded cedar bark, deep leaf litter, anything that traps a lot of air.
It's the trapped air that does the insulating, right?
them.
Not the material itself.
Exactly. The R value, the measure of thermal resistance, comes from the tiny pockets of still air within the material. So the key is depth and dryness.
How deep are we talking?
Not just a thin layer. The guidelines suggest your compressed floor bedding should be at least a foot thick. And the walls, maybe several feet thick, packed with debris. We're talking serious volume.
Wow, okay. That's a lot of gathering. What about the shape of these structures? Does that matter?
Hugely important for efficiency. You want to minimize the surface area through which heat can escape relative to the internal volume you're trying to keep warm.
So like a sphere or an egg shape?
Perfect examples. Domes, refined wickiups, low-profile rounded shapes, they have the least surface area for their volume. A big square or rectangular shelter has lots of flat surfaces and sharp corners where heat loss, especially through convection currents, is much higher.
So these microclimate shelters are typically compact, low to the ground, and very, very thick-walled.
That's the essence of it. Designed to hold on to every bit of generated heat. Extremely effective in very cold conditions.
Okay, makes sense. Now the third type, durable A-frames, specifically built on snow hills. This sounds like a combination of structure and location strategy.
It absolutely is. Let's break down the location first on snow hills.
Why a hill? Wouldn't that be windier?
Potentially, yes. But
Yeah.
valleys and low-lying flat areas are what survival experts call cold sinks.
Cold sinks.
Yeah. Cold air is denser than warm air. It flows downhill like water and pools in the lowest spots. Overnight, the temperature down in a hollow can be significantly colder, dangerously colder, than just 50 or 100 feet up the slope. So building slightly uphill gets you out of that layer of super chilled, stagnant air.
Exactly. It's a major thermal advantage, especially on clear, cold nights when that cold air drainage is most pronounced.
Okay, but back to my question. The wind. Hills are usually windier. Doesn't that cancel out the temperature benefit?
That's where the structure comes in, the A-frame. It's chosen because it handles wind and snow load so well.
How does the A-frame shape help?
It's steep angle, ideally around 60 degrees, is fantastic at shedding snow. Heavy snow just slides off, it doesn't build up and crush the shelter.
Right, less surface area for snow to sit on.
And it's inherently strong and stable against lateral forces, like wind pushing on the side. It's a naturally braced shape, much more robust in high winds than, say, a simple lean-to or even some dome shapes.
So it's a trade-off. You accept potentially more wind exposure on the hill.
To gain the significant thermal benefit of avoiding the valley cold sink, and you use a structure specifically designed to withstand that wind and associated snow load. Got it. So durability is key for this type. What does that mean for construction?
It means a really solid ridge pole is essential. That's the main beam at the peak. And it needs to be supported by strong end structures, often tripods, anchored firmly into the packed snow or frozen ground beneath.
So it's leveraging the ground slope but needs a robust frame.
Yes. Maximum strength, minimum material, designed to work with the terrain and resist the specific environmental stresses of that location, wind and snow.
Okay, so we've got the blueprints for the three main types: elevated, insulated, and the A-frame on hills. Now let's zoom back in a bit. Section 3 is about the techniques that seem to underpin all of these builds, right? The insulation and the build quality.
Exactly. These are the universal principles that make Brotherwood's shelters work, regardless of the specific design. Let's revisit those natural insulating layers first.
We talked about needing depths and dryness. How do you actually achieve that practically when you're out there?
Sourcing is the first challenge, especially finding dry stuff in a wet forest. It takes knowledge and, again, patience.
Where you look.
Under natural shelters. Think deep under dense evergreen trees where rain doesn't penetrate much. Beneath large rock overhangs, especially south-facing ones that get some sun. Sometimes even inside hollow deadfall logs, the outer wood might be damp. But the core can be surprisingly dry.
Looking for nature's dry pockets.
And you need material that feels light, airy. The source mentions like dry cornflakes, not heavy, damp, slimy leaves.
Okay, so you find the dry stuff, then how do you apply it? You mentioned fluffing it.
Yeah, absolutely critical. You don't just pile it up. You need to handle it, shake it out vigorously, let any remaining moisture, dirt, or compressed clumps fall away. You want to maximize the air trapped within the material. Loft is key.
Creating as much trapped air as possible.
Right. And when you put it down, say for floor bedding in an A-frame or the walls of an insulated shelter, you often layer it.
Layering, how so?
But maybe a base layer of slightly damper, more compressed material to fill gaps near the ground. But the top layer, the one you'll actually sleep on or that forms the inner wall, that needs to be bone dry and really deep, keeping it as lofty as possible.
It sounds meticulous.
It is. It takes time. Reinforces that whole patience theme again, doesn't it? Rushing the insulation means a cold shelter.
Okay, insulation sourcing and application. What about the second technique? Building with durability and insight.
This goes back to the idea that these aren't just temporary emergency shelters. The source implies they're built to last, to withstand real environmental stress over time.
Which requires precision.
Yes. Precision in things like lashing, which we touched on, ensuring every joint is tight and secure. Using the right knot, figure 8, square lashing for the specific type of joint to maximize its load-bearing capacity.
So the cordage needs to be pulled really tight.
Almost singing tight, as some descriptions put it. Any slack, any play in the joints under load, that's where failure starts, especially in strong winds or under heavy snow.
And insight here means more than just following instructions.
It means actively reading the environment and using it to your advantage during the build. We talked about finding that naturally forked branch.
Right, using natural shapes.
Or finding the perfect flat rocks for a stable base. Another key example of insight is entrance placement.
You mentioned that briefly with the A-frame, avoiding the wind.
Exactly. You need to observe the landscape, feel the prevailing wind direction, understand how it might funnel through terrain. Then you position your shelter's entrance on the leeward side, the sheltered side.
Makes a huge difference to heat loss, I imagine.
Massive difference. And related to that is entrance size. Insight dictates keeping it small, just big enough to get in and out.
Why small?
To minimize air exchange. Warm air wants to rise and escape. Cold air wants to seep in low. A small entrance, maybe with a simple flap made of bark or woven branches, acts like a valve, controlling that exchange and keeping the internal climate stable.
It's like basic architectural principles applied with natural materials. Understanding airflow and thermal gradients.
That's a great way to put it. It's building with vision, not just following steps.
Okay, so tying this all together for the listener, if someone's not planning a wilderness survival trip next week, why is learning about Brotherwood's methods useful? What's the bridge to, modern life?
That's always the important question, isn't it? I think it's because these skills, this knowledge, it really transcends the context of just building a shelter in the woods.
How so?
Well, at its core, it's a deep dive into material science, understanding the properties of wood, stone, leaves, air, how they interact, how they perform under stress. It's about engineering efficiency. Learning why that natural fork is stronger than a poorly made joint teaches you about optimizing connections and managing stress points in any system you might design or manage.
Whether that's software code or a business process.
Could be, yeah. And the resource management aspect, learning to prioritize the easy, effective resources like dry deadfall instead of wasting huge energy on difficult ones like greenwood. That's fundamental efficiency. That applies everywhere in logistics, project management, personal time management.
Right. Maximize results, minimize wasted effort.
And fundamentally understanding insulation, that the real value comes from trapping still air. That's basic energy conservation knowledge. It applies to how we build our homes, how we think about heating and cooling.
So this stuff resonates whether you're interested in, say, wildlife and nature, or maybe more in primitive technology and engineering history.
Exactly. It hits both interests. It's practical skill meets historical knowledge meets fundamental physics.
Okay, let's try and wrap this up then. A quick summary of the key takeaways from this deep dive into Brotherwood's unseen shelter techniques. We covered 3 pretty distinct engineered solutions.
Yeah, first was the elevated platform. That's your answer to ground moisture, dampness, snow contact, using that air gap as a thermal break.
Got it. Second, the insulated structure. Think compact, rounded shakes, super thick walls of dry debris, all about creating that warm microclimate inside.
Holding on to heat. And third, the durable A-frame. Built strong to handle wind and snow and strategically placed on hillsides to avoid those dangerous valley cold sinks.
So 3 shelters, 3 strategies. But it feels like the bigger lesson isn't just what to build, but how you approach it.
Absolutely. The real takeaway seems to be embedded in that philosophy. That effective survival, or maybe just effective building, isn't about panic or brute strength. It's about mental discipline.
Patience.
Patience to do things right, meticulously.
Respect for nature.
Which translates into smart, sustainable resource use.
And that trained eye.
Seeing the potential, the opportunity, the utility in every piece of the environment around you.
Right, which leads us perfectly into a final thought for you, the listener, based purely on these sources. If true survival, or maybe true effectiveness in any complex task, demands that patience, that respect, that ability to see opportunity in what others discard, what material, what overlooked skill, what resource that seems like debris in your own world, your work, your life, are you maybe currently failing to see the potential in? What could you process and utilize more effectively to build something? Well, something lasting.
That's a good question to ponder.
Something to think about. Until next time. Thanks for joining us for this deep dive.